This is you. You are building a simple 2D game. Your game has enemies, like this goblin for instance. When the goblin gets hit by the player, you want to show a blood spatter effect to satisfy the player's need for violence. Naturally, the blood effect should spawn in the same position the goblin is in when it gets hit. So in your code, you write something like this. After instantiating the effect, you set its position equal to the goblin's position and then add it to the scene. And lo and behold, why did it spawn over here? Has something like this ever happened to you? Don't lie, I know it did. What you should have done is use global position instead of position, except that sometimes you don't. You could also have used the goblin's parent's LocalToWorld matrix to transform the position before assigning it for whatever reason. Sometimes using the LocalToParent matrix can also work, but not always. If most of what I just said sounds like gibberish to you, or you no longer want to trial and error your way through this process, then grab a drink, sit down, and let me tell you about the wonderful world of coordinate spaces. What they are, all the math that's involved, and how all of this relates to this stupid blood spatter effect spawning over here when I clearly set its position to equal the goblin's position. For crying out loud, are you actually kidding me right now? Pretty much any game engine, graphics program, or animation library has the concept of a scene tree. The scene tree contains all objects in the current scene and allows us to define a hierarchy between them. For instance, in this scene, the spear node is a child of the hero node. In order to understand why our blood effect spawned in a completely different place than we expected, we need to understand what the actual implications of this parent-child relationship are. From working with a game engine or graphics program, you probably know what the practical effects are. Once a node is parented to another node, it will be affected by all of the parent's transformations too. For example, when we change our hero's position in the scene, either by dragging it around or setting its position in code, the spear node will always stay in the same location relative to the hero node because it is a child of the hero node. This is super useful since it allows us to position the spear only once without having to worry about updating its position manually every time the hero moves. The same goes for scaling and rotating the parent too. So that's why we use object hierarchies, but how does this actually work? When we transform the hero, the spear's position also changes. How do game engines or graphics programs figure out what the spear's actual position is so that it can be drawn in the correct position on screen? I believe that one of the best ways to learn a topic is to try and implement it yourself, so let's give it a shot. Let's consider a simple scene with a rectangle and a circle in it. In our scene tree, we have set the circle as a child of the rectangle node. When we move the rectangle around, the circle should move around with it, so that it always stays in the same position relative to the rectangle. Similarly, when we scale or rotate the rectangle, the circle should get scaled and rotated by the same amount. To make things a little more concrete, let's say the circle should always be 300 pixels to the rectangle's right and 200 pixels above it. So really, all we're saying is that the circle's position will be whatever the rectangle's current position is, but shifted 300 pixels in the positive x direction and 200 pixels in the negative y direction. Remember that in computer graphics, the y-axis points from top to bottom. That's why we have to move in the negative y direction in order to visually position the circle above the rectangle. We can also express this as a vector. This vector is the circle's relative position with respect to the rectangle. All a relative position is the desired offset from the parent's position. Conversely, a node's actual position in the scene is its absolute position. What we're trying to do is figure out what the circle's absolute position is based off its relative position. To do this, let's define a formula with two parameters, the rectangle's current position P and the circle's relative position R. To get started, all we need to do in order to figure out the circle's absolute position is add its relative position to the rectangle's position. Now, when we move the rectangle around, we can use this formula to figure out where the circle should be drawn. This formula is still pretty simple, and we're going to see in a second that it's also far from complete, but it's a good start. What this formula is describing is a transformation. It's taking in a point P and returning a new point that's shifted over Rx on the x-axis and Ry on the y-axis. These kinds of transformations are usually written as a transformation matrix. It might come as a bit of a surprise that this matrix is a 3x3 matrix, even though we've only been talking about 2 dimensions so far. Without going into too much detail, this is because it allows us to later compose these matrices together by multiplying them. If we were to use a 2x3 matrix, for instance, then by the rules of matrix multiplication, we wouldn't be able to multiply them. For the same reason, we're also expressing the 2D coordinates of our relative position as a 3-dimensional vector. The z component of the position vector will always be 1, so it won't affect the result of our calculations. If you were to actually implement this in code, you would simply discard the z component of the vector at the end of the calculation, so this is more of a mathematical implementation detail. If we were to multiply this out, we would end up with the exact same vector as before, again ignoring the z component, but this is a much more idiomatic way of writing it. There's an interesting thing we can learn from the formula even in its current incomplete state. Watch what happens to the circle's relative position when we move the rectangle around. The relative position doesn't change, and looking at the formula we can also see why. Moving the rectangle only changes the value of p. R is still the same. The relative position is just the desired offset from the parent's position, and this offset doesn't change just because the parent moved. Regardless of the position of the rectangle, the circle should still be 300 pixels to the right and 200 pixels above. So unless we want to change the offset to the parent, meaning move the circle around, the relative position is going to be constant. This fact that a node's relative position is unaffected by its parent's transformation is a surprisingly important insight that we will come back to later in this video. But for now, let's get back to the issue at hand. Next up is scaling. When we scale the rectangle, its position doesn't change. This means that using our current formula, the circle also wouldn't move. What we want to happen is something like this, however. In this video, we're only concerned with an object's position, so we're going to ignore the fact that the circle's dimensions clearly also need to change. A different way to think about this is that when we scale the rectangle, we also want to scale the offset or the distance between the two objects by the same amount. Luckily for us, this is about as straightforward as can be. All we have to do is multiply the circle's relative position, its offset from the parent, by the rectangle's scaling factor. In a transformation matrix, scaling is controlled by these two entries, controlling the horizontal and vertical scaling respectively. Replacing these two entries with the rectangle scale gives us a matrix that looks like this, where S sub x is the rectangle's horizontal scaling factor and S sub y is the vertical scaling factor. Let's add the rectangle's scaling factor as a parameter to our formula and also add our new transformation matrix. Multiplying two matrices together has the effect of applying one transformation after the other. Think function composition. So if we multiply them together, that gives us a new transformation matrix that not only calculates the desired offset from the parent's position, but also scales it by the parent's scaling factor. The last thing we have to implement is considering the rectangle's rotation as well. This is slightly more complicated than translation or scaling, and the notation can get a little dense, but we'll build this up one step at a time. Let's start out by only considering rotation. For now, let's assume that the circle has a known position of 300, -200. Conceptually, what we want to do is that as we're rotating the rectangle in place, we also want to rotate the circle's position around the rectangle by the same angle. A transformation matrix for a rotation looks like this, where theta is the angle of rotation. However, this is for a rotation around the origin, and we want to rotate around the rectangle's position. This sounds a lot more complicated than it actually is. The way you rotate around an arbitrary point is kind of brilliant in its simplicity. It's made up of 3 parts, each of which can be represented by its own transformation matrix, where P is the point we want to rotate around. First, we perform a translation so that the point we're rotating around now sits at the origin. This effectively eliminates our special case, and we're now back to just rotating around the origin, which means we can use our regular rotation matrix. And then afterwards, we simply undo the initial translation. And voila, we have rotated the circle around the rectangle. If we combine these 3 transformation matrices into one matrix by multiplying them, we end up with this. the transformation matrix to rotate around some arbitrary point P by some angle theta. Now, this transformation matrix is correct, but it's more complicated than it needs to be for our use case. There's actually a way for us to use just the basic rotation matrix instead. First, let's decompose this matrix again into its individual transformations, and then add it to our existing formula. Let's also decompose our existing transformation matrix from before into its translation and scaling matrices. You might have already noticed that there's something a bit weird going on here. Let's step through these transformations one by one and see what we're actually doing at each step. First, we take the relative position and scale it. Then we translate the scaled position by adding the parent's position. And then we immediately undo this translation as part of our rotation before translating the point by the parent's position again after the rotation. These two matrices are inverses of each other, so they end up cancelling each other out, and we're left with this much more reasonable looking formula. Notice how we're still performing all the same transformations, however. We're still scaling, rotating, and translating the relative position. The thing that changed, however, is the order in which we perform them. Before, we rotated the position after we had already translated it, but that meant we had to compensate for that translation in our rotation, because after translating, our point is no longer relative to the origin. Which is why we ended up with this more complicated rotation matrix. Now, we're rotating the point before translating it, which means we can use the regular rotation matrix because we're still rotating around the origin. This is also a nice example that illustrates why matrix multiplication is not commutative. We just saw that the order in which we apply the transformation matters. We can then multiply our three transformation matrices together to end up with our final transformation matrix. All that's left to do is to update our formula to also take the rectangle's rotation as a parameter. Now, depending on your level of familiarity with linear algebra, this might still seem like a bit much to take in all at once. But if I did a good enough job explaining, you hopefully understand what this matrix represents, regardless of its notation. This matrix is a combination of three distinct transformations: a scaling, a rotation, and a translation, just expressed as a single transformation. That's the beautiful thing about matrices, they compose. We can express this pretty intricate process as a combination of several much simpler transformations. So using this formula, we can now figure out the circle's absolute position regardless of the rectangle's transformation. In fact, we can figure out the absolute position of any relative position as long as we know the parent's transformation. So that's pretty cool, I'd say. Well done. Let's look at this relative position a little closer because it's still a bit weird. It looks like coordinates, but they also don't directly map to a position in our scene. Instead, we have to do this whole matrix transformation song and dance to get the real location from the relative position. So how exactly should we interpret them? So far, I've said that we can think of the relative position as describing the offset from the parent. Take whatever the parent's position is and add another 300 pixels in the x direction and subtract 200 pixels from the y direction. As if that's some special case property of these relative coordinates. But that's how all coordinates work. It's literally what coordinates are. They describe an offset from some known point of reference, usually called the origin. When I tell you that some object has the coordinates 100, 200, you implicitly understand that that's relative to wherever 0, 0 is. See, coordinates are always relative. They have to be. You cannot describe a position in space without a known point of reference. If I tell you that the rectangle sits at coordinates 200, 200, that doesn't mean anything unless you know three things: where 0, 0 is, the directions the axes are pointing, essentially knowing which way is right and which way is up, and what the unit length is. If I have to move 200 pixels along the x-axis, I need to know how big one unit is. Position, rotation, and scale. Sounds kind of familiar, doesn't it? All that to say that relative positions aren't anything special. They're completely normal coordinates. It's just that their origin, their point of reference, is different. they exist in a different coordinate space than their absolute position counterparts. See, there's nothing saying that you can only have one coordinate system. I already mentioned that all we need is the position, scale, and rotation of the origin, and then we can construct a coordinate space around that point. And that's exactly what's happening here. Every object in our scene has its own coordinate space defined by its position, rotation, and scale. Think of it as a grid where the object sits at its center. This combination of position, rotation, and scale is also called the transform of the object. When we make an object a child of another object, we're essentially moving it into the parent's coordinate space. We're changing what the origin is that its coordinates are relative to. It's now positioned on the grid around the parent. This is why the relative position is also called the local position, and why relative coordinates are also called local coordinates, because they're local to the parent's coordinate space. Conversely, the topmost coordinate space in our scene is called world space. When we're talking about absolute or global coordinates, we're talking about coordinates in world space. With this in mind, there's another way to visualize why local coordinates don't change when the parent's transform changes. Here, we have the same scene twice, but viewed from two different coordinate spaces. On the left, we see the scene from world space, so pretty much as we would normally see it. On the right, we're viewing the scene from the point of view of the circle, which lives in the rectangle's coordinate space. Watch what happens when we move the rectangle around. In world space, everything looks as expected, both the rectangle and the circle move accordingly. But from the point of view of the circle, its position didn't change at all. It's the world around it that moved in the opposite direction. When we moved the rectangle, we moved its entire coordinate space along with it. So for our circle, nothing has changed. The origin is still wherever the rectangle is, and 300 pixels in the positive x direction is still exactly where it was before. Similarly, when we scale the rectangle, we're scaling its entire coordinate system. So nothing changes in local space. It's everything else that has gotten bigger or smaller. 300 pixels in the positive x direction in local space is still here. It's just that these same 300 pixels don't get you as far anymore in world space. And lastly, when we're rotating the rectangle, we're rotating its entire coordinate space along with it. So 300 pixels along the positive x-axis in local space is still here, it's just that in world space, that same axis is now pointing in a different direction. Let's look at our transformation matrix from before again. This matrix actually has a name. It is called the LocalToParent matrix. It's called LocalToParent because it takes a position from local space of the parent, our relative position, and computes the equivalent position in parent space. Parent space is essentially the local space of the parent's parent. We're moving up one level in our scene tree. Multiplying the local position with the LocalToParent matrix gives us the coordinates that point to the same position on screen, but expressed relative to a different origin. Here's how we can visualize what's happening. First, we take the local position as is, and without any changes, interpret it as a position in parent space. So in parent space, 300 negative 200 would be here. Obviously, unless local space and parent space happen to be identical, this points to a different position on screen. What we have to do is apply all transformations of the original local space to this new position. One way to think about this is that by taking the position out of local space, it is now affected by all the transformations that were applied to its original parent. And that's exactly what the LocalToParent matrix expresses. Remember, this matrix is a combination of three individual transformations. First, we're scaling the position by whatever the parent scaling factor is. We're applying the scaling transformation of the original local space to the position. Next, we're rotating the scaled position around its new origin by the same angle by which the parent is rotated. We're applying the rotation transformation of the original local space to the position. And lastly, we're translating the scaled and rotated position by the parent's position. We're applying the translation transformation of the original local space to the position. And there we go. We took the local position and calculated its equivalent position in parent space. One thing that's important to realize is that this matrix is called LocalToParent, not LocalToWorld. Multiplying a local position by the LocalToParent matrix only moves us up one level in our scene tree. In this example, because the circle's parent is already a top-level node, moving up one level actually moves us into world space, but this isn't a general rule. Say we added another object to the scene, but this time as a child of the circle. We're adding one level to our scene tree. If we multiply this object's position with the circle's LocalToParent matrix, this would give us a position in local space of the rectangle, not in world space. We're only moving up one level in the scene tree. If we wanted the world space coordinates, we would have to repeat this process until we eventually reach a top-level node. What this tells us is that there is no single local-to-world matrix. The local-to-world matrix is different depending on an object's position in the scene tree hierarchy. It is the result of recursively multiplying the local-to-parent matrices of each of an object's parents. So far, we've only talked about going up the scene tree, going from local to parent space. So it would be reasonable to wonder if there's also a parent-to-local matrix. And yes, there is. It is literally the inverse of the local-to-parent matrix. The same goes for the world-to-local matrix. You would first have to calculate the local-to-world matrix, as we've discussed, and then take its inverse. In practice, you won't ever really have to do this by hand, because your game engine or graphics library will take care of this for you, but there you go. So, knowing what we now know, let's finally go back to our example from the beginning, the blood spatter effect that spawns in the wrong position. Here's the code we wrote. And importantly, here's the scene tree for the scene. Notice how we're accessing the position of the goblin's sprite, not the goblin node itself. This means that the position we're getting back is not going to be in world space, but in local space of the goblin node. The local position in this case happens to be 0, 0, right in the center of the goblin node's coordinate space. This is fairly common for sprites because you usually don't want them to be off-center. We then use that position to set the blood effect's position, and you might already be able to tell where this is going to go wrong. When we add the blood effect to the scene, it gets added as a top-level node, meaning it's in a different coordinate space than the goblin sprite is. So we're using a position from local space of the goblin node, but interpret it as a position in the coordinate space the blood effect is in, which in this case is world space. And, well, 0, 0 in world space happens to be here, in the top left corner. By now we also know that as long as we don't move the goblin's sprite, this position will always be 0, 0, regardless of the position of the goblin itself. So even when we move our objects around, the blood spatter effect will always spawn up here, at 0, 0 in world space. There are several ways we could fix this problem. Instead of using the goblin's sprite's position, we could use the goblin's position directly, since it is also in world space. Or we could keep using the goblin sprite's position, but compute its world space position by multiplying it with the parent's LocalToParent matrix. Depending on the specific tool you're using, there's most likely also a way to get and set an object's world space position directly. What all these solutions have in common is that we're ensuring that the position we're assigning to the blood effect is in the same coordinate space the blood effect will be in after we added it to the scene. And this is really the main takeaway from all of this. Whenever you're dealing with coordinates and you want to compare them or otherwise do math with them, you need to make sure that they are actually in the same coordinate space as each other. Otherwise, your math will most likely come out wrong. And trust me, this is a very easy mistake to make. I ran into the exact same problem probably 100 times just while making the animations for this video. But hopefully, you're now better equipped to understand what's happening and why it's happening, as well as knowing what to do to fix the issue. Oh, and speaking of animations, I used a fantastic open source tool called Motion Canvas to make the animations in this video. Links to the source code of this video as well as the Motion Canvas website itself are in the description below. That's all I got for you folks. Thanks so much for watching, and if this video is any indication, I'll see you in about half a year for another video. No promises though. Okay, bye.